In this tutorial, we will be learning how to solve for the area under the curve of a line using trapezoids, left-endpoint rectangles, and right-endpoint rectangles. Y equals x squared for 0 is less than x, which is less than or equal to 5, and the area under the curve is split into 4 intervals. Find the areas of all of the 3 trapezoids and the triangle, and then add the respective areas together to find the total area under the curve. So the trapezoid method works well for some problems, but in problems that have curves with larger areas, it can take a long time to calculate and add up the individual areas. Luckily, summation notation gives us a way to estimate area under the curve without having to add up all of the individual sums. When using summation notation, we use left or right endpoint rectangles to estimate the area. Left endpoints look like this, and right endpoints look like this. Notice that left endpoint rectangles are drawn from the left endpoint of the interval. Since these rectangles are drawn below the line, an estimate using left endpoint rectangles is going to be of lower value than what the actual area under the curve is. Since right endpoint rectangles are drawn from the right endpoint of the interval and are therefore above the line, the estimate will be of a higher value than the actual area. The first step in using right and left endpoint rectangles is to find the widths, or the bases, of all of the rectangles. The width is found by observing the change in x. Find the change by subtracting the smallest number x can be, in this example 0, from the largest number x can be, in this example 5, and dividing the difference by the number of intervals, in this case 4. For this problem, each interval should have a change in x of 1.25. Therefore, the width of each rectangle will be 1.25. Okay, now we are ready to use summation notation. This is what a summation notation looks like. This weird-looking symbol right here is the Greek letter called sigma. These two numbers, right here and right here, are the indexes. The one on the bottom gives us the starting value of x, and the number on the top is the last value of x. Starting with the bottom number, plug the x value into the equation on the right of the sigma. Then, plug in the next whole number value of x into the same equation and add it to the last equation. Keep plugging in the whole number values of x until you have plugged in the top index as a value of x. Sigma notation is an easy way to approximate the area under the curve because it is much faster than adding up individual areas. Let's use sigma notation with left endpoint rectangles to find the area under the curve. The first step is to find the heights of the rectangles. To find the heights of left endpoint rectangles, start at x0 equals 0. Keep adding the base value that we previously found to find each new height. So x1 equals 0 plus 1.25, which equals 1.25. x2 equals 1.25 plus 1.25, which is 2.50, and on. Since the pattern of change is 1.25 each time, the equation of change in height can be written as 1.25x. Now we have everything we need to create our summation notation for this problem. The general equation of a left endpoint rectangle is right here. Now this looks really complicated, but when we break it down, it is easier to see how this really does describe the area under the curve. X of k is the equation that we just found for the change in height. We can plug this equation into our original equation to find f of x of k. We also already know that change in x is 1.25. N minus 1 is just the number of x's minus 1, so we know that this is 3. And we know that in left endpoint rectangle problems, the k is always equal to 0, or the x in this equation. Now all we have to do is program it into our calculators and solve. Now let's try it with right endpoint rectangles. Notice that the width and the height are going to be exactly the same as before, so you don't change that part of your summation notation. All you're going to change is your indexes. When using right endpoint rectangles, the first value of x isn't 0, it's 1. The number of xk's is the same as in the left endpoint method, which is 4 for this equation. But the top index is the actual number of xk's, and we don't subtract 1, so it's just 4. So this would be the final left endpoint summation. So all you have to do is plug it into your calculator and solve. Okay, now let's say that the x-axis represents time in hours, and that the y-axis represents miles per hour. In that case, the area under the curve would represent miles. Why does it represent miles? Well, an area of a rectangle can be described as width times height. So in this problem, we would be multiplying some number in hours by some in miles per hour. If we do that, the hours will cancel out and we'll be left with miles. And that's the end of this tutorial. Thanks for watching.